Welcome to Hydrocarbons Part 5. In this video lecture, we are going to look at chirality, limiting the exploration to what's really relevant for allied health students. Chirality is just a very key, important topic because our biochemistry is almost entirely chiral. And so let's get busy and see what that means. Now, remembering from our introduction to isomers that constitutional or structural isomers, right? That's the same chemical formula with different connections. And so, for example, like here we have C6H12, same chemical formula, but look very different. And then we've studied then stereoisomers. I think these are the most challenging, right? Because they have the same connectivity, same chemical formula, right? But different spatial arrangements. So this is where we have to bust out our brain yoga and visualize things in 3 dimensions. And this can be where it's very helpful to get that molecular model kit to build your ability to see. So let's quickly review here, right? So conformations are just about rotation, right? So these are actually the same compound with different rotation. And then we could look at, remember geometric? That's where we have the cis trans. And that could be alkenes or cycloalkanes. And we covered that pretty thoroughly in a previous video, so I think that that's enough said there. So now this is the new part. This is where we talk about chirality, and they're enantiomers. And so we have to have a chiral carbon. And what is a chiral carbon? A chiral carbon is a tetrahedral carbon, right? And so we know what tetrahedral means, right? Tetrahedral means that it has 4 single bonds, and each of these bonds is going to be a different group. Right, so a tetrahedral carbon bonded to 4 different groups. So let's go ahead and use our tetrahedral geometry, right? Making our 3-dimensional shape, right? The straight lines are in the plane, the wedge is poking out, the dash is going back, right? And then just the 4 different groups, just symbolically A, B, C, D for now. Okay? So chiral carbons they have a lot of names. They're very important. They can be called a chirality center. They can be called a stereo center, since they're stereoisomers. They can also be called asymmetric carbons. So don't let these names bother you or fool you. Just, expand your vocabulary. And so in the same way that we built flashcards for like our ions and our conversion factors, it could be helpful for you to get some flashcards going for the different types of isomers to make sure that you have them down. So let's look at a couple examples of what is and what is not chiral. So 2-butanol, right? But is a 4-carbon chain, and then coming off of carbon 2, we have the alcohol. And then for this example, I'm going to put the hydrogen here because this is our chiral carbon. If we look at this chiral carbon, we see that it has a methyl group, an ethyl group, a hydrogen, and a hydroxyl, right? So there's 4 different groups bonded to this chiral carbon. Let's compare that to 2-propanol. In 2-propanol, here's our 3 carbons. We have our alcohol coming off the 2nd carbon again. But when we look here, right, so we see there are no chiral carbons because these groups are the same, right? So the hydrogen's different and the hydroxyl's different, but since these 2 are the same, achiral. So when you see A in the front, it means not chiral, right? Like asymmetry means not symmetrical. Alrighty, so now let's take a minute and let's look at some models and help to bring some experience to this. So here is the simplest set of models right here. I'll hold these up for you. There we go. Okay, so if I turn it, there we go. So you can see that, notice that there's a mirror image, right? So we've got a methyl group on the top, and then they see the white and the green and the orange, all right? So this carbon in the center is a chiral carbon because it's bonded to 4 different groups: the white, the green, the orange, and the methyl group. Now there's something very interesting about chiral carbons. They are mirror images, but they're like our hands in that they're non-superimposable. If I try to overlay these and I line up like the hydrogens and the methyls, look what happens, right? The oranges and the greens don't line up. And let's see. Yeah, so just like our hands, let me hold my hands up here for you. Oops, there we go. Okay, here's my hands, right? So here's the mirror image, right? So the mirror plane's going down the center, right? So if I try to overlay my hands, right, my thumbs aren't going to work. The idea is, have you ever put your shoes on the wrong foot, right? You ever put your right foot into a left shoe? It doesn't fit. It's because our feet are chiral. All right, now let's look at those models a little more closely. All right, here's the 2-propanol. Okay, so here's the, right, the 3 carbons and the alcohol group. Now we can put this together and we'll see that we could have a mirror image. All right, but the difference here is if I flip this one over, they're imposable. I can line everything up. Right? We can line up the hydroxyl groups, we can line up the hydrogens, and we can line up the methyls, right? That's why we said 2-propanol is not chiral. We can always show a mirror, we can show a mirror image of anything, right? But it's superimposable. Let's look at one last set of models. This would be the 2-butanol. So let me make sure you're oriented, right? So here's our 1, 2, 3, 4 carbon chain, right? So we have the methyl and the ethyl and the hydrogen and the alcohol group. So when we put these together, right, here's our mirror image. Let's see if I can rotate that. Right, so you can see we have the mirror image, right? And if I try to impose them, if we line up the methyl and the ethyls, notice how the hydroxyl and the hydrogen don't overlap. And if we flip it and we line up the hydrogens and the alcohol groups, now we've got methyls and ethyls, right? So let's go back to our notes now. When we look at enantiomers, right, they always come in pairs. And the pairs are the mirror images. So, and we'll build that as we keep going through the notes. Alrighty. So, so there's an introduction to chirality. And now the first skill that we want to build is when we look at a compound, we want to be able to see the chiral carbons. And this can be particularly challenging for our class because we're looking at rather complex molecules, and so it can be a little tricky. So if we look here, right, so CH3, CH2, CH2, so none of those are chiral because we have more than one hydrogen. But when we get right here, right, and this is where it can be a good idea to draw in any missing hydrogens if we think that it's chiral. So when we look here, we can see, here there's 3 carbons, there's a propyl group. And then here's 4 carbons, that's a butyl group. And then a hydrogen and a hydroxyl. So this carbon is chiral, put a little star. It's bonded to 4 different groups. CH3, CH2, CH3, none of those are an option. If we look right here and we add the hydrogen, right, Now we see we have a methyl and an ethyl and the hydrogen and the bromo. So 4 different groups. So there's our chiral carbon. So basically we just want to look for the branches. But we don't want to get complacent though. We have to keep our critical thinking, because if we come here we're like, oh, there's a branch. But notice that this carbon, these are the same. So this carbon is not going to be chiral because it has 2 methyl groups coming off of it. Remember that a chiral carbon has to have 4 unique groups. But if we keep moving along, here would be our chiral carbon. It has the methyl, the ethyl, and then this big honkin' thing here, right, the biggie. And then last but not least, of course, the hydrogen. So there would be our chiral carbon. Here, if we don't see branches, we know not to worry. We get here, we look around. This is definitely going to be a chiral carbon, right? So there's the ethyl, and then another biggie, and another biggie right there, and then of course the hydrogen. So that's the first chiral carbon, and then this one's pretty tricky because there's actually 2. Here's the second chiral carbon, right? There's our methyl and our ethyl, and then a super biggie, and then of course the hydrogen. All right, so we had 2 centers here, and then, oh my goodness, cholesterol. There's 8 chiral carbons. All right, so here's the challenge. You know there's 8. This would be a great place to pause the video for a minute and see if you can find all 8, and then we'll compare answers. Alrighty, let's see how you did. Right, these are the same. CH2, CH2. Oh, there's a branch. This is definitely a chiral. Okay, and then when we get to this ring, the rings can be very tricky, right? If we look at this carbon, we see it when we branch out, right? This is a CH2, and then this carbon's bonded to 4 other carbons. So that pen's a little fat. We're going to go with this, right? So there's our second. CH2, CH2. Anytime we see a branch, right? So if we look at here, right, this goes, notice that these 2 carbons are different. This is a CH2, and then this carbon's busy bonded to a lot of other carbons. So this is also chiral. Same thing with this one here, right? Methyl group, 6-membered ring, 5-membered ring, lots of differences. So not all, even though they're carbons, the carbons are different. Okay, same thing here, right? Part of a fused ring, part of another fused ring by itself, hydrogen. Okay, so we got 1, 2, 3, 4, 5, 6. We only got a few left right here, right? Methyl, and then these other carbons are different. And then last but not least, right here at the hydroxyl group. All right, so there's the 8 chiral carbons of cholesterol. And this is our most challenging. We won't get any more difficult than cholesterol. And we'll practice this in class together as well. So just know that this is our goal, right? But right now, if you're more comfortable working on like A, B, and C, that's okay. That's a great place to start. And with a bit more practice, you'll be able to look at more complicated molecules and identify all of the chiral carbons. All right. Now let's have a little review here, a little nomenclature review, and then weave in there what we've been learning about chirality. So we're going to draw the skeletal line structure for 3-ethyl, 4-methyl hexane, and then we're going to star any chiral carbons. All right, so remember, we want to start at the end of the name, hexane. That tells us we have 6 chiral carbons, or six carbons. And then if we number these, okay, coming off of carbon 3 is an ethyl group. That's 2 carbons and a methyl group. All right. So let's go across and see if we can find chiral carbons. So CH3, CH2, Ooh, this one looks like it has possibilities, but this is where we have to step back. Notice that carbon 3 has 2 ethyl groups coming off. So since those are the same group, carbon 3 can't be chiral. But let's move on to carbon 4. Aha, here's our chiral carbon, right? We have our methyl and our ethyl, and then our biggie. And then of course we can't forget sweet little hydrogen. Alrighty, so hopefully you starred carbon 4. There's our chiral carbon. And now we're going to look a little more closely at enantiomers and see how to draw them. So as I mentioned on the first page, right, when we have one chiral carbon, we're going to end up with a pair of enantiomers. And when you look at the names of different drugs or compounds, if they have chiral centers, you will see RS, little l, little d, plus or minus, or DL. And they always come in sets of 2 because they're pairs. And so we're not going to be responsible for naming these, but when you read a name, if you see any of these terms at the beginning of the name, it's letting you know that there's chiral carbons. And then here's the butanol. I did my best with the models, and we'll work together in class that we see that we have the mirror image. And so we can use the perspective formula that we've been used to drawing to show the chiral carbons. And we're going to introduce a new type of drawing now. This is called the Fisher. And so with perspective formula, you could think of it as like a side view, looking at a profile. And with the Fisher projection, we can think of it as a direct view. And so from now on, when you see structures written in this cross form, the horizontals are wedges. Okay, so the horizontals, right, poke out of the paper with the wedge. And I like to think of it as like they're reaching out to give us a hug. Horizontals are hugs, right? They're coming out of the paper. And then the dashes, the vertical lines are the dashes, and those are going back into the paper. So the verticals go back into the paper. Okay, so it just minimizes having to draw the wedges and the dashes. So this is now called a Fisher projection. All right, so when we are talking about chiral carbons, we could draw them using the perspective formula or the Fisher projection. And we want to be able to draw, right, since they come in pairs, if we're given one enantiomer, we want to be able to draw the pair, right? So we're going to have our pair of enantiomers. Alrighty, so now this would be a good minute. I want to show you something with my hands. All right, so when we look at our hands, we have the mirror image, right? So the mirror plane is coming right through the middle, okay? So notice that like the mirror's in the center, my thumbs are closest, my pinkies are farthest away, and my fingertips are at the top, right? So when we do a mirror image, right, whatever's closest to the mirror stays closest to the mirror. And now if I poke my thumbs towards you, notice I have the mirror image on both hands and both thumbs are pointing towards you. If I put my thumbs back, both thumbs are back. So we have to think about, we've all looked in mirrors, but we might not really have thought about what a mirror image means. So basically a mirror image means, right, if my pinkies are farthest from the mirror, they stay farthest from the mirror. So now that we've practiced with our hands a little bit, let's see if we can apply this to the paper. All right, so if we're drawing the mirror image, right? If something's at the top, it stays at the top. So the CH3 group's going to stay at the top, right? And then think the hydrogen would be like the pinky, right? It's going to continue to poke out. Everything, these were all in the plane of the paper, they stay in the plane of the paper. The wedge stays a wedge. The OH is close to the mirror, it stays close to the mirror. The bromine is on a dash, it stays on a dash, and it's also there. So these are the pair of enantiomers for this compound coming off of that chiral center. I think the perspective formula is probably the trickiest. The fissure is a little more straightforward. So with the fissure, now this is our chiral carbon right here in the center. Okay, so all we're worried about is the orientation around the chiral center. So at the top here, this ethyl group, we can just write that as we always would. We don't have to make that into a mirror image because it's not chiral. And then right at the top and the bottom, right, the fingernails stay at the top, the wrist stays at the bottom. There's the hydrogen, right? So the mirror image comes from this methyl group was closest to the mirror, and the bromine was furthest from the mirror. All right, so now this is our second pair of enantiomers. So in our class, you'll be responsible if you're given one enantiomer, then you want to be able to draw its partner, the other pair. And that's where we'll stop with that part. We're going to look a little more closely at enantiomers because they have such an important biological significance. Another way that enantiomers are described is they're called optical isomers. And so optical in this sense has to do with light. So enantiomers are very fascinating. They have the same boiling point, melting point, density, refractive index. That's how they bend light, right? How soluble they are in water. But where they differ is how they interact with polarized light, right? So that's different. This is rotating light. And so quite literally, Louis Pasteur was sitting there with some tartaric acid, and tartaric acid exists as a pair of enantiomers, and he noticed that the light, there was something happening with the light. And so ultimately we were able to do experiments where we could take light and we could put it in a polarizing monochromator and then a polarizing filter. And here if we had one enantiomer, not the pair, but if we just had one enantiomer, we could measure that the light was rotated, right? So here it was vertical up and down, and now we see that it's been rotated, right? So the light is rotated. And so what we want to know, the last thing we really need to know about enantiomers is they come in pairs, and one enantiomer is going to rotate light clockwise, and the other enantiomer is going to rotate light counterclockwise. And that's why they get called optical isomers. So as you continue on your journey through the science and the allied health field, if you come across the term optical isomer, I don't want it to throw you for a loop. I want you just to understand that it's talking about this phenomena of enantiomers. It is possible to have a one-to-one mixture of the enantiomers, and that has a special term called a racemic mixture. So let's make sure that, and this is the last thing that you need to know about enantiomers, and then we have one last page of practice problems, right? So here's glucose, right? That'll be important when we study biochemistry. D-glucose rotates the plane polarized light plus 52.7 degrees. So what would be the rotation for L-glucose? Right? Well, we know that they rotate equal and opposite. So if D-glucose is going in the clockwise direction, then L-glucose is going to go in the counterclockwise direction. But because they're enantiomers, the value will be the same, just right. So D-glucose goes clockwise and L-glucose goes counterclockwise. Alrighty. And then to make sure you understand the definition of a racemic mixture, right? So if we had plain polarized light and we put it through a racemic mixture of D and L-glucose, that means it's 1-to-1. What happens to the light? Basically, there's no net rotation. All right? So half of the sample will rotate the light clockwise, and the other half of the sample will rotate the light counterclockwise, and so they cancel out. Okay. And now let's look at our last page, and I've been mentioning and emphasizing that there's a lot of biochemical applications, so let's get a sense of those to see why we care so much about chirality. All right, it's because the enantiomers will have different, in most cases the enantiomers have different biological effects, right? So here's our buddy vitamin C. Let's look at vitamin C and go ahead and star the chiral carbon. All right, let's see how you did, right? So there it is. This would be our chiral carbon, right? This can't be the chiral carbon because it has 2 hydrogens. And, oh, actually, we have 2 chiral carbons, right? And then this would also be a chiral carbon here. Okay, so we have 2 chiral carbons. That's awesome. All right, and we're going to put our emphasis on this one right here. So in this, and here's our mirror plane, okay? So this is the vitamin C that's a nutrient, right? When people aren't feeling well, they'll say, oh, I should take a little bit of vitamin C, help me feel better. It's a good antioxidant, right? The enantiomer has little to no biofunction. Okay, so only one enantiomer really supports our nutrition. The other one is just along for the ride. Another example would be thalidomide. So I'll give you guys a moment to star the chiral carbon here. Right, so it has to be tetrahedral. There we go, it's right here. Okay, so there's our chiral carbon. Now, thalidomide has a very interesting history. Here's the pair of enantiomers. This enantiomer here relieves nausea and was prescribed, I think, late 50s, early 60s in Europe for women that were pregnant because they had morning sickness, and this enantiomer did a great job of relieving nausea. Unfortunately, in the body, it isomerized into its enantiomer, and the enantiomer is a teratogen. And what a teratogen does is it causes mutations in fetuses. And so shortly after, within less than a year of them prescribing thalidomide to relieve nausea, infants were being born with the flipper hands and feet with these mutations from the thalidomide. So it was quickly taken off the market. Ultimately, though, thalidomide is being used in a cancer treatment. I have a friend who was diagnosed with a blood cancer back before 2000, and none of us thought that she would even see the new millennium. And she is still alive, and in part she's due because she does take thalidomide, but she's not going to get pregnant and she's not going to have any kids. Over time, though, she has started to feel numbness in her fingers and toes. So there is something about this enantiomer that affects our limbs. And there are scientists out there looking at it more closely. one last example of chirality, THC, the psychoactive ingredient of cannabis. Here's the long name. So here I'd mentioned about the R's and the S's. That let us know that there's chiral carbons. Here's how it rotates light. Because it has chiral carbons, there's an enantiomer, but the active form is 13 to 230 times more active than its enantiomer. And the interesting thing about cannabinoids is they're also produced in our body as endocannabinoids. So so as we explore the medical value of cannabis, we'll be looking more closely at this. But for here, we'll just practice starring the chiral carbons. So I'll give you a moment. And as we look along, right, anytime we see the straight chain or double bonds, no chirality there. We've got matching methyl groups here, no chirality here either. But this carbon and this carbon, right, there's our two chiral carbons on THC. All righty. So that wraps up our video on enantiomers. I know it's a lot, but hopefully with those last couple pages you see how important this is to our biochemistry, and you'll take a few minutes now to work the practice problems to reinforce your understanding.